Hello, everyone. In this video, I'm going to go ahead and go over Chapter 21, Electrostatic Force. I went over this, of course, in discussion section, but some people I'm coming to realize, especially in Physics 2, like to review it again, go over it again. So I had quite a few people asking me, although the other video goes over Chapter 22, I didn't post anything here that actually goes over Chapter 21. So I'm going to go ahead and go over it. There happen to be 3 problems on the homework on this, but we still need to know how to do these force problems regardless. All right, so let's talk about the electrostatic force. So the definition of the electrostatic force is F equals K QQ over R squared. And this is not like a robust mathematical definition just yet. But the truth is that, of course, the force is a vector. And this equation is going to allow us to find the magnitude of that vector, so long as we input the absolute values for the 2 charged objects that are experiencing this force from one another. So the corollary that I relate this to is a gravitational force, universal gravity from Physics 1, where you have gmm over r squared. It's going to function very similarly. The one thing we need to be concerned with here, though, is that charge can be positive or negative in this topic, right? We have positive or negative charge, and that will give us either an attractive or repulsive force. So, for instance, if I have 2 charges, one positive, one negative, in this case, we're going to have an attraction between these 2 objects, and so the force will pull each particle toward the other. If I have a positive and a positive, or a negative and a negative, in both of these cases, we're going to have a repulsion. And so these particles are going to push each other away, like that. And the way that we're going to proceed with problems in this section is to, first of all, use the sign convention to establish a direction for our forces. Step 2 is going to be to actually calculate the magnitude of each force between 2 charged objects using KQQ over r squared. And then step 3, which I haven't put here, but step 3 is to consider the fact that this is a vector. So in summing up several forces on a single particle, you have to sum the forces in the x and sum the forces in the y. And then if you need to find an angle for a force, you'd have tangent of theta is equal to the net y force over the net x force. All right. So great. So that's going to be our approach. Let's go ahead and just sort of jump into some problems. So the first one is a little bit of an easier level difficulty, which is great. We want to start off just sort of getting everything moving. And we have 4 charges in a square, 4 charged objects, charged particles in a square. And the square has side lengths A. Cool. So we'll go ahead and draw them. We have 1, 2, 3, and 4, and those are the respective names. So 1, 2, 3, and 4. And and as I mentioned, the side length is A here. We'll go ahead and label that. And what they're going to ask us to do is just to find the net electrostatic force on particle 3. Particle 3 happens to be this particle down here. And our rule says that each particle, each of the other 3, 1, 2, and 4, will exhibit a force on particle 3. So, as I mentioned, our first step is to assign the directions to the forces using our sign convention. All right, so first thing we need to do is determine if these charges are positive or negative. I don't care about the actual numbers just yet. I just want to know what's positive and what's negative. All right, so 1 is positive, 2 is negative, 3 is positive, 4 is negative. So if I have the same sign, it'll be a repel. If I have opposite signs, it'll be an attract. We'll just go ahead and go around the circle, starting with particle 1. Particle 1 is positive, particle 3 is positive, so that will be a repel. And I've labeled this F sub 1, which is just to tell me that this is the force due to particle 1. And of course, I know it's on particle 3 because I've attached the vector arrow there. Next up, we have particle 2. Particle 2 is negative, particle 3 is positive, so that will be an attraction. And we'll go ahead and call that F3. And then particle 4 is negative, particle 3 is positive, so that will also be an attraction that'll go to the right. So that's F4. All right, so I have these 3 different forces. My next step is to calculate each force using KQQ over r squared. And remember, we're going to do magnitudes, right? So we're just going to use the positive values. And we can go ahead and write out what they would be. So we have F1, the force between 1 and 3. That's going to be K times the absolute value of Q1 times the absolute value of Q3. Q1 creates the force, Q3 experiences it. And then we divide by the square of the distance between them. Well, my distance is just the side length A. That'll be A squared, and I can calculate that. K here, by the way, is 8.99 times 10 to the negative 9. It's also 1 over 4 pi epsilon naught. But I'll go ahead and write that somewhere. We'll go ahead and put that right up here. 8.99. Come on, let me have a 9. Every time I get too close to the margins, it freaks out. Okay. Times 10 to the 9th. Great. It's a little wonky there, but okay. Just for your notes. Okay, so great. So that's F1. We also have F3, F4. So let's go ahead and calculate those. Well, they're going to look very similar. F3 is going to be K times the absolute value of, I guess that should have been labeled F2, because that is the force that is created by particle 2 on particle 3. So we'd have the absolute value of Q2, which creates that force, 2. Absolute value of Q2 times the absolute value of Q3. And then we divide by square the distance between them. Now, the distance between them is not just a side length. Our side length is A, but these two are separated along a diagonal. So along a diagonal, you have the side length times the square root of 2 for a square as the length. So this will be A root 2 squared. All right, and then the last thing is our force F4. F4 is equal to K times the absolute value of the charge creating this force is Q4. So we have Q4 times the absolute value of Q3 that is experiencing the force over the distance between them, which is, again, just a side length. So that'll just be A squared. All right, so we've punched in all our numbers, calculate all those things. Maybe you would wait to do the actual calculation until the next step. But the last step here is to find the net x and net y. So in doing this, we need to consider to start, if we want to do the sum of the x components, we have to consider which forces have an x component. So for starters, F1 is all in the y direction. It's all up and down. So it has no x component. You'd have only an x component from F4, which is actually the entire thing because it all points to the right. And then you also have an x component of F2, where this angle theta will give us the x component. And since F2 points along the diagonal of a square, that theta is 45 degrees. So for the x component, we'll have cosine of 45 on F2. And putting that all together, we then have the net x force is equal to F4 plus F2 times cosine of 45. And again, we have F4 and F2 on the last page. I'll leave the actual calculation up to you. Now, that will be the net x force. For the net y force, we instead have the component of F2, and then we're also going to have all of F1. Now, here's where we need to keep in mind our sign convention for the directions, where we have right is positive x, left is negative x, up is positive y, down is negative y. The y component of F2 is going to point upward because that force points up and to the right. So we'll have a positive y component for F2. But since F1 points downward, that's going to give us a negative y component when we go to do the force summing here, the superposition. So we sum the forces in the y direction. As I mentioned, up we have a positive F2. The y component will be sine of 45. And then down we have that F1, so we subtract F1 downward. And then we plug in the corresponding forces that we calculated on the last page, and then we solve from there. Okay, so we went through our steps again just to refresh with what those steps are. Step 1 is draw a picture to determine if your forces attract or repel. Step 2 is to calculate the actual magnitude of each force using kq over r squared. And then step 3 is the superposition principle, where you sum your x and y components, just as we did in physics 1 with vectors in physics 1. So that's sort of, as I said, kind of an easy, nice entryway problem. The next problem is a step up in difficulty, absolutely. And we're going to go ahead and tackle it. So what's going on in this problem is you start off with some arrangement, and then you're going to move one of the particles. When you move one of the particles, the force is going to change. So first of all, here's what our arrangement looks like. We have a particle at the origin, and then we have four other particles, 1, 2, 3, and 4. So we label them 1, 2, 3, and 4. And all of these charge values are given in terms of E. So I just want to mention what E is. It's not the electron charge. E is the elementary charge, and it has a value of 1.6 times 10 to the negative 19th coulombs. It is a positive value. The electron itself has a negative charge of 1.6 times 10 to the negative 19. So the electron charge is negative E. This E stands for elementary, not electron. I like to reiterate that a few times throughout the semester, but just mention it right here. So in this problem, particles 1, 2, 3, and 4 are all going to have a charge of negative E. So what's important is we need to know that it's negative so we can do our directions. And then particle 5 at the origin is going to have a positive charge. And we're going to investigate the force on particle 5 at the origin. So to start, what was step 1? Step 1 is to label our directions for the force from each of the other 4 particles. In each one of these cases, we have positive and negative, so we're going to have an attraction. Particle 5 is going to be attracted to each of the other 4 particles. So we go ahead and, whoops, try that again. We have an attraction here, we'll call that F1. Attraction here will be F2. Our attraction here will be F3. And our attraction here will be F4. And we can calculate each of these if we'd like to. One thing that I will mention right now is that, of course, as we proceed through this problem, we're going to change the position of particle 1, and then we're going to change the position of particle 3. So maybe we want to indicate something here that those are unknowns, all right? But so I'm going to actually kind of do those in pairs. So let's start with F1. F1 is going to be a magnitude. So I'm going to do K, absolute value Q over R squared. So what is that going to give us? It'll be K times the absolute value of particle 1 that's creating the force has a charge of negative E. Particle 5 that's experiencing it has a charge of positive E. Those are both in absolute values though, so of course you'll just end up with KE squared on top. And then on the bottom, I have the distance from the center particle out to particle 1. So I am going to write this as R1 squared. The reason I'm doing it as R is just to remind myself that we have a variable location there. Okay, we'll come back to that though. But simplifying on top, notice that I'll have KE squared. So I have KE squared on the top, and on the bottom, I just have R1 squared. Okay, continuing around, if we want to do F2, this is going to go kind of similarly. On the top, we're going to have K times the absolute value of negative E times the absolute value of positive E. For all of these, we're going to have the same thing. So for all of them, we're going to end up with KE squared on top. And then the bottom, we have the distance from the origin to that particle. Well, again, with particle 2, we're keeping particle 2 fixed in the same location. So we can go ahead and write down Y2. Y2 is a given, and it's not going to change. For F3, we're also going to move F3. So I'm also going to leave a variable distance variable here, or a distance variable that is allowed to change. So I'm going to use KE squared over, again, R3 squared. And then the last one is particle 4. So for F4, by the same argument as the other 3, we have KE squared on top. And by the same argument as we had on 2 right here, particle 4 is not going to be moving, so we can go ahead and just plug straight in Y4 squared. Okay, so we have all these set up. And I know that my next step is to do the superposition and to plug everything in. What I want to do in this problem, though, is I'm going to have this initial arrangement, and then I'm going to move particle 1 first. And when I move particle 1, I want to rotate my particle. I'm sorry, I want to rotate the net force 30 degrees counterclockwise. So I am changing an angle. If I'm changing an angle, it means that I want a delta theta, which is equal to theta final minus theta initial. And I wanted to rotate it 30 degrees counterclockwise. Counterclockwise in this class is always a positive direction, so it'll be positive 30 degrees. Okay, so this is the equation that I ultimately want to work on. I need to find my initial angle, of course, then I can find my final angle. In either case, the way that you find the angle is with the definition that we have. Nope, I think it was back here. The definition that we have for tangent. Tangent of theta is the total y over the total x. So in order to do that, I first have to sum my forces in the x and the y, and then I have to do my total y and my total x in a ratio. Okay, so we'll go ahead and do that. Notice that these forces all point either entirely in x or y. So in the x, we have F3 minus F1, and in the y, we have F4 minus F2. So that's actually going to give us some decently clean equations to work with. So summing the forces in the x, as I just mentioned, I have F3 minus F1, and I can actually go ahead and express those as KE squared over R3 squared minus KE squared over R1 squared. Remember, those R's mean that we're going to change those values, but yeah, okay. But for now, we're good there. And yeah, summing the forces in the y direction, then we have our F4 up minus F2 down. And we can go ahead and substitute in those values that we calculated on the last page. Those values are KE squared on Y4 squared minus KE squared on Y2 squared. Okay, last thing I wanted to do was to set up a ratio and use our tangent of theta. Of course, we don't know what theta is initially, but we know that in general, tangent of theta is going to be the total y over the total x. So we'll have this stuff here on top over this stuff here on the bottom. And notice that when I subtract, I'll have a KE squared and everything. So I can go ahead and cancel that out. So I'm doing that cancelization right here in this setup for the ratio. And so all that we're left with in the y is 1 on y4 squared minus 1 on y2 squared. And then on the bottom, we'll have 1 on r3 squared minus 1 on r1 squared. Okay, so we just have y over x here. When we do y over x, we do this one over this one. And when we do that, we can cancel out the KE squareds. So now we just have a matter of the locations of the particles and relating it back to a theta. If I want to find my initial theta, what I would do ideally is I'd say that I want theta initial, and then let me actually do some colors here. So I'd want theta initial, and I would just need to plug in for R3 and R1 the initial locations of particle 3 and particle 1, which those are given in the problem as x3 and x1. So for theta naught, I'd plug in R3 equals x3 and R1 equals x1. However, when you do this, because x3 is the positive value and x1 is just the negative of x3, since they're like opposite, since they're both squared, you're actually going to get a 0 on the bottom, which will be undefined, and your calculator won't know what to do with it. So you have to actually sort of do this reasoning on your own to arrive at what this means. What does it mean for those two particles to have equal but opposite, 1 over r squareds? Well, what that actually means, if we go back, that means that here, the KE squared over r for these two, when you subtract them, those are actually canceling out, and those are going to 0. So what does it mean to have an initial x component of 0? That means that we only have y component initially. And then the only question is the y component positive or negative? Because again, our x is 0 because R3 and R1 have the same magnitude. So we only have y component. So then in order to figure out if our initial direction is up or down, that's the only answer that we need, right? Is it up or down? Well, that's just going to depend on what the sign is on the y component. If it's positive, it's up. If it's negative, it's down. So you can plug those in if you need to, but a very quick argument that'll get you there is to see that particle 4, although it has the same value for the charge as particle 2, it's much closer to the origin. So that means that the force that 4 is pulling up with is going to be larger than the force that F2 is pulling down with. Okay, so again, you could do that calculation if you'd like, but I'm just going to keep going here. I'm going to proceed with the knowledge and the realization that theta naught is straight up, which is 90 degrees. If it were the other one, if it were straight down, then theta naught would be 270 degrees or negative 90 degrees. Okay, so I have my theta initial. Now I know that I want to rotate that theta initial 30 degrees from this equation right here. I know I want to rotate theta initial by 30 degrees. If I plug in my 90 right there, what do I have? I have theta final is equal to, I should say theta final minus my theta initial, which is 90, is going to be equal to 30, which tells me that my theta final is 120 degrees. So what I want to do is I want to move particle 1, I want to move particle 1 first. So I want to change this R1 and I want to produce an angle of 120 degrees. So I'm going to let R1 be the variable here. I'm keeping R3 fixed where it is. So for R3, I'm going to go ahead and plug in X3, and that will thus give me something like tangent of 120 is equal to all this stuff over here with R3 substituted out for X3. So just to write that down, it would be 1 on y4 squared minus 1 on y2 squared over 1 on x3 squared minus 1 on x1. Oh, no, that's actually going to be r1 because this is going to be the unknown that we're solving for. Cool. So again, we know the two y's in the numerator. We know the x in the denominator. We're solving for r1, but I'll leave that algebra up to you. Be very careful with your algebra here as you solve, but you should be able to solve for r1. When you do solve for r1, you're going to get, your calculator is going to tell you r1 is equal to something like 0.05 or whatever. And if you put that down, you're going to get a wrong answer. Here's why. There's an implicit plus or minus because we're going to end up taking a square root and solving the square. So when you take that square root, remember, if you take a square root in an equation, you have a plus or minus. And so it's up to you to determine whether the answer there is the positive or the negative. And because particle 1 is on the negative x-axis, we know that we want a negative value for its location. So we will take the negative value. In part B, we want to keep particle 1 at that new negative value. We now want to move particle 3. And as we do this, we want to rotate the direction of the field back to where it was. So for part B, we want to go from 120 degrees back to 90 degrees. How do I get back to 90 degrees by changing R3 now? Well, I'll plug in the R1 that I already have, and I'll solve for R3. But again, when I try to do tangent of 90, I'm going to get undefined. So to flip this problem around, you could say, okay, if I want to make this fraction undefined, that means I need to have a 0 in the denominator. So 1 on R3 squared, 1 on R3 squared minus 1 on R1 squared has to be equal to 0, where R1 is the answer that I had from part A. And if you solve this, what you'll see is that R1 and R3 are equal in their squares. But since R3 is on the positive x-axis, you end up with a positive value for R3. And so what is the overall solution here? Well, we get our total answer, our complete answer right here. The negative value is R1 because it's on the negative x-axis, and the positive value is our final location for particle 3, our final R3. And that's what will cause those two to cancel out again and to rotate us back to 90 degrees vertical for the electric force. Okay, so those are our two charge distribution problems. We have one more charge distribution problems. This one is a little different than the others. And this is just a problem that's been on the homework forever. It has a very specific procedure. And let once every 5 semesters is on an exam. So if you know how to do the procedure, it's actually not that difficult. But just keep in mind that yeah, you just need to sort of learn how to do these procedures and just do this problem. Make sure you're good with it and comfortable with it. So this problem has 3 charges. The values of the charge are given in nanocoulombs. So remember that's 10 to the -9. And our side length is given in centimeters. So that's 10 to the -2. We have to use coulombs and meters. But okay, so we're going to start off with these 3 particles. Our particles are A, B, and C. And they're going to have some initial charge on them. So my initial charge is going to be, I don't love that. Oop. Sorry, I'm trying to get too fancy here. Okay, so my initial charge on A is, say, -3, and it's nanocoulombs, but I'm just going to use the numbers because we just need to use the numbers here. So -3, -4, and +8. Okay, so I'm going to do a series of operations. Either I'm going to connect the particles or the spheres, these conducting spheres. I'm either going to connect them by a wire and then disconnect them, in which case the charge will balance between the two. Or I'm going to ground one of them, which means that the charge will go to 0 and be canceled out. So my first operation is I take particle A and particle B and I connect them by a wire and allow them to come into equilibrium. When I do that, my total charge on each should be the same. Why is that going to happen? Well, you have one is at -3, one is at -4. Some charge is going to leak from one to the other until they meet and they balance in the middle. Mathematically, the way to do it is just add it together and divide by 2. Just take the average. So what is that? -3 plus -4 is -7. Divided by 2 is -3.5. Cool. And then we haven't done anything to C, so we'll just bring that down, keep that 8 nanocoulombs on charge C, or sphere C. All right, next up, we're going to take particle B and we're going to ground it. When I ground particle B, all that I'm doing is just removing the charge, and we will be left with 0 nanocoulombs. We do not do anything to A or C in this step, so just go ahead and bring down their charge values. And then the last step is to connect B and C by a wire, allow them to come into equilibrium, and then detach the wire. So I have 0 on B, 8 on C, 0 plus 8 is 4, 0 plus 8 is 8, divided by 2 is 4, and so we end up with 4 nanocoulombs on each. And A hasn't done anything in this step, so it still has that -3.5. All right, and then as I said, these are all in nanocoulombs. These are all 10 to the -9th coulombs. But if I want to calculate the force between any two of them, I just need to pick the corresponding charges and do KQQ over R squared, where my R here is actually D. So for part A, I want to find the initial magnitude of the electrostatic force between A and C. That'll be -3 and 8 for part A. For part B, I'm asked to find the force between A and C after I've done all these operations. So that would be my -3 nanocoulombs and my 4 nanocoulombs. And then part C, they ask me to find the force between B and C. So you'd use your 4 nanocoulombs and 4 nanocoulombs. And in each of these cases, as I mentioned, you'll have KQQ on the top, and on the bottom, you'll have R is equal to that D with that separation. There's nothing funky going on with D. They just sort of, they just sort of let us have that one uh, and not be, a part of the difficulty of the problem. So, all right, there you go. That's the 3 electrostatic force problems. And then there's another video up for the electric field. And I will also be posting the Gauss's law videos. I have the first one recorded, and it's actually going to be 2 parts for Gauss's law. But yeah, if you just keep your eye on the YouTube channel, then you should see it when it goes up. All right, if you have any questions, feel free to, of course, as always, send me a message on Canvas. That's going to be your quickest and easiest way to hear back from me. So, all right, have a good day, everybody.